There we go. Okay, so my name's Humphries. I'm a security consultant at Gotham Digital Science based in London. And
Yeah, I'm also a security consultant, but I'm based here in Zurich. And yeah, we both work for the same company.
yep, so Gotham Digital Science is based over sort of 3 continents, almost 4. APAC, Europe, and America.
Yes.
So what we're going to be talking about is down to you.
So basically, smart contracts are so hot right now. So basically, we've been doing some research on the security of smart contracts, specifically around. Basically, we've been doing some work around the security of smart contracts, and we've basically implemented and designed a suite of tools that we can be used for reverse engineering and automated analysis of smart contracts. And then with this, we've basically taken a snapshot of the blockchain at a given point in time, and we've ran our tool against this. Against the framework that we've built, and basically just gathered out a summary of the state of secure or vulnerabilities on the Ethereum blockchain at the moment.
Great. And then to give you guys just a bit of background, we've got 2 logos on the slides here, Gotham Digital Science and Aon. So what happened in 2016? GDS, Gotham Digital Science, got bought out by a company called Stroz Friedberg, who does digital forensics, IR, and due diligence. And then sort of midway through 2017, it was then, Stroz Friedberg then acquired by Aon. So from here on, you'll see occasionally the 2 logos. We still run as Gotham Digital Science, but we are as part of the Aon family. So what we're going to be talking about, what we're not talking about even, we're definitely not talking about the politics, so we're not going to go into what altcoin is best, or what you can do with different coins, or even the politics of the Ethereum blockchain. We're definitely not going to be breaking the cryptography. We're not mathematicians, so we didn't even look at that. We kind of just trusted that those guys knew what they were doing. And we're not going to be looking at the EVM. Whilst we have implemented the EVM, but we're not actually looking at how the EVM can be broken. There are plenty of good clients out there already that are pretty good at what they do. So that's kind of not the scope of this talk. So now we're going to be looking at sort of the Ethereum background.
Basically, regarding Ethereum, we're not focusing on Ethereum itself, we're looking at the smart contract component. And the smart contract component, basically, if you're not familiar, it provides a different paradigm for programming, and basically allows developers to write completely decentralized code. So this code is stored on the blockchain, and it's fully decentralized. And then when it comes to execution, this code gets executed on all of the nodes. And basically, we're allowed to decentralize code running, which allows us to do some cool things, basically. EVM, it stands for Ethereum Virtual Machine, and this is where the actual bytecode that gets compiled down executes it on. And there are a few different implementations of this. You've got the primary ones such as parity and geth. But we're not really going into the specifics of that. We're more just looking around what the EVM can do for us. So in terms of how the EVM is architected, it's basically a stack-based architecture, and it has a stack size of 1024 limit, and that's basically made up of 256-bit words. It's basically they call it Turing complete, but it's only really quasi-Turing complete because of you can't basically do infinite loops, and this is due to the gas cost. So there's basically transactions are paid for in gas, so each instruction that gets executed inside the EVM has a gas cost, and there's basically a gas limit, and this is basically how it prevents certain attacks and basically allow the computers executing the opcodes that they receive this. It basically forms the transaction fee. And then on top of this, it has an independent storage module, ideology. So basically, the Persistent storage is basically formed of the state of the contract, and each contract has its own state, and this is where persistent storage is held. So if a contract holds addresses of participants that are taking place, it's basically stored in there. And then it also has memory, which is just a byte addressable memory storage.
Okay, and we'll move on to sort of some of the inbuilt restrictions and security that exist within the Ethereum blockchain. So as Elliot touched on the gas usage, so the gas usage is quite a intrinsic part of the Ethereum blockchain, and it actually can be used to prevent the denial of service attack. So the gas requirement on a contract restricts the amount that a potential attacker could use and abuse the Ethereum blockchain to prevent a potential outage. Programs may only interact with each other in the form of a single arbitrary bytes array. So they're not actually, the Ethereum contracts that are running are not actually able to communicate with each other through any other way, so they can't sort of go through the EVM in sort of a backdoor kind of way. Everything is sandboxed on the EVM. There's no way that it can break out onto the user's machine that is known. I mean, obviously this presentation isn't going into the EVM security. So from what we know at the moment, there is no way that you can actually execute anything on the host machine that's not within the EVM. And the EVM is fully deterministic. This does produce some issues that we will go into later. So it does restrict the fact that randomization is a big problem at the moment within the Ethereum blockchain, and we do touch on that. Because everything needs to be fully deterministic, it's actually quite hard to have something that can produce a random number accurately produced multiple times. And to give you guys sort of an overview of what the architecture compared to sort of a standard application or traditional application, if you're not fully aware, at the top there you've got your traditional, I can do this, you've got your traditional front end that could be written in JavaScript or C# or whatever what you like. You've got a back end of Node, and then your data stores Postgres. And then you can look at the Ethereum chain, and again you have a front end of JavaScript. This can be used as your distributed app, or DApp as they're known. This is not quite correct. Like there'll be some people that say that this isn't correct at all, because the smart contract and blockchain are basically one and the same. But to provide sort of an understanding of how it actually works, this is quite a nice way of viewing it. So you can see that the smart contract is almost like where the server is, where your functions are performed, and then the blockchain is where everything's stored.
Yeah, cool. Yeah, so basically with the Ethereum contracts, they're basically, there's a primary language called Solidity, and this is the main language that smart contracts are developed in. So the language was inspired by C++, JavaScript, and Python. It types a little bit like JavaScript, people say, but it's really not anything like JavaScript. It just looks a little bit like JavaScript when it's written out. It's a statically typed language, again, so that's one thing that's completely different to JavaScript. And basically this gets compiled down to EVM bytecode, and that's typically with the Sol-C compiler. And it's also important to note that Solidity isn't the only programming language for the EVM blockchain. So there's others such as Serpent and Viper. But Solidity is definitely the most common one, and most developers for smart contracts are typically using Solidity. And for one of the main reasons we're also focusing on EVM bytecode specifically is this allows us to analyze contracts written in multiple different languages. So in terms of the tools that we've made, they don't care about if it's written in Solidity or Viper. It basically, just those compilers compile down to the EVM bytecode, and we work on that instead. So yeah, I think that's it from this one.
Okay, and here's just a quick snippet of a Solidity code example, just to give you guys that may not have encountered Solidity before, just a quick look at actually how it would sort of look. We will be giving some Solidity code snippets throughout the presentation, so we will explain them as they go, but it's not too difficult to understand. So to start this off, we set out some ideas that we wanted to achieve. And one of them was obviously the creation of a tool. And then we sort of said, well, can we then scan the blockchain with that tool? And yeah, you can. We definitely had some objectives. We wanted to collect the binaries that were being run. And then we wanted to store them in a way that we could then easily query those binaries to then use the tool against. And then, fairly fast and repeatable. That final objective was actually fairly fast, is not something I would say that the Ethereum blockchain is definitely capable of. Repeatable, yes. Fast, no. And then we stood some context around those contracts as well, just to give us a little bit of information that we could then sort of refer back to and do some fancy graphs and charts and that kind of thing. So in terms of the actual development of this scanner, we wrote it in Python 3 using the IPC interface, and we actually use Geth for that, which is the Go Ethereum implementation of the EVM. So that just runs on your local machine. I believe it's the IPC flag on Geth you can run. I can't quite remember. And it just spins up an IPC interface that you can directly call using the Web3 interface for Python. And that works really well. You can multi-thread it, and it will fly through the blockchain pretty quickly. As of then, I think it wasn't entirely smooth. So the Ethereum blockchain, when we scanned it, had over 5 million blocks at the time, and that's a lot of data. And as you can say, the hardware can't keep up. So what I found in my initial tests of this was the hardware that I was running the Ethereum blockchain on wasn't quick enough. And I did a little bit of research around it. And it turns out that you actually need an SSD and a fairly fast processor and internet connection to catch up to and continue on with the Ethereum blockchain syncing. And this was my experience. Your mileage may vary. I just thought I'd give it as a little bit of information. But as I put there, a fast sync, which is it's cutting out a lot of the tree nodes within there. It's about 80 gigabytes in size and took 3 days. And that was on a DigitalOcean VPS with 4 cores and a 500 gig SSD. It took a while. So a few stats of our blockchain scanning. I'm going to have to actually read these off because I can't remember offhand. We found just under 1.5 million contracts on the blockchain, and that's within 5 million blocks. Empty contracts is just under 60,000, and we could probably put that down to either self-destruction or out-of-gas exceptions. The out-of-gas exceptions will happen during the execution of, say, a contract creation. So what you'll find is that there's potentially still a contract creation pushed onto a block, and that ends up with just an empty contract. So we've got unique contracts of just over 76,000. So what we did is we took a hash of all of the contracts within that we found within the database, and then just distincted them and stuck them in another table, just so we could scan those, so we weren't duplicating ourselves. The largest contract that we found was on just this block, just over 5 million. That's a contract hash that I'm sure you guys are going to remember off by heart, and that was just 49,000 bytes. And then we've also got our most duplicated contract at 361,000 total implementations of this contract, and that was seen at the first block number of 424 quadruple 1. So it just gives a little bit of information of the scanning that we did and what we actually pulled out. I found these stats quite interesting. We got a graph later that shows the vulnerabilities over time and how they may or may not increase or decrease.
Yeah, just to point out as well, the length for the longest contract, that would probably be half due to the ASCII hex that we're storing. So yeah, obviously each 2 characters represents 1 byte. Yeah,
good point. So now we're going to be introducing the tool that has been created for the contract scanning. But first of all...
Yep, so this is my cat, and she's been helping me do my research by basically sitting over my laptop and trying to eat my printouts of the Ethereum yellow paper, and just being very helpful. So yeah, she's just been helping me do my research.
Everyone needs a mascot and loves cats, so...
What happened then?
Is this one?
Okay, yeah. So yeah, basically the tool, we have the name Treacle Mine. One of our colleagues came up with the name, and we couldn't think of anything better, so we've stuck with that. And basically, it's an automated security analysis tool for EVM bytecode. It's open source, so it's not open sourced yet, but this is something that we'll be doing in the future, and it'll be released under the GPL2 license. And it's basically an extensible architecture. So we want developers to be able to easily contribute and easily incorporate this into their own like development tool chains and any tools that they're using for part of their development processes. So yeah, one thing, it's developed in JavaScript, which is something that I kind of regretted after. But the reasons behind it were because JavaScript is going to be it's going to be a language that's very familiar to developers of decentralized applications. Typically the front ends for these apps are written in JavaScript, and a lot of the tools and frameworks for the Ethereum ecosystem are based around JavaScript. So basically, it's going to be more accessible to smart contract developers, even if it gives us some headaches during the process. And yeah, so it's a completely pure JavaScript. Like this is designed to fit into the tool chains, as I've already said. It completely runs within the browser, which is nice. And yeah, it's designed to fit into these tool chains, so they can easily, during their development lifecycle, they can analyze the bytecode and pick up any issues that are maybe there quite early on. And it's comprised of 3 components currently. So we have initially an EVM disassembler. So this basically just disassembles the bytecode, and this parses out all of the instructions and all of the basic blocks within that bytecode. And then we have a partial EVM emulation engine. So the emulation engine at the moment, it doesn't emulate everything, but we emulate basically all of the stack manipulation instructions. We emulate these fully. We don't emulate storage currently or memory addressable space. And then we have the a vulnerability scanner, which basically fits on, it can plug into the EVM emulator. So as we are running the emulator, we can basically do static and dynamic analysis of the opcodes that are there and values that are placed on top of the stack. So just yet more about the architecture. So yeah, we convert obviously the instructions, parse out the bytecodes. We emulate the internal EVM state. We keep track of variables on the stack, and basically, because we're not fully emulating EVM, when we reach certain opcodes, like we want to be able to track these across the stack, and we basically just have a simple tagging mechanism. So if, for example, a value gets pushed onto the stack from a specific opcode, so if we say that the block hash opcode is executed and that pushes up a block hash to the stack, like in this case we're not actually executing a block, so we don't have a real block hash, so we just push up a magic value, and we tag this value to say that this is come from the block hash opcode, and then we can basically track this through the execution. So then if we do any like arithmetic operations on this opcode, we're basically going to keep track, and we know that the output of this operation was basically tainted by this block hash or this user input. And that's basically just a summary of like how we go over the emulation. Like we're not going into too much detail, we're more focusing on the actual issues and the results. But yeah, we basically process all of these instructions, and then the plugin it has a plugin architecture. So once we have the emulator, we can basically register, we can plug in the EVM vulnerability scanner, and within the vulnerability scanner we can register new detectors or signatures. So yeah, we basically just have a very simple way of doing that. So this is just the rough skeleton of the vulnerability scanner. And basically, yeah, it's very simple. We have a register function, register signature function, and this just stores off in an array of signatures. And then during the execution and the EVM emulation, we invoke process instruction, and then we invoke all of the different signatures, and then they can have their own independent logic, and they're completely separated. And that's just at a high level how we're implementing this.
Okay, so a big topic at the moment is definitely responsible disclosure. So a lot of vulnerabilities will get disclosed, and then they're immediately pushed out onto the web for everybody to see, and the entire community goes, "Whoa, what are you doing? That's really irresponsible," and we agree, as is apparent. So what we're actually going to say at the moment is we're not going to tell you any contracts that have vulnerabilities. We're not going to be telling you where the vulnerabilities exist in those contracts. Whilst we do have that data, we're not going to be publishing it. We'll be publishing the tool, so you guys can then discover the vulnerabilities yourself, but we're not going to be actively publishing that data, purely because we don't think that would be responsible disclosure, purely because the Ethereum blockchain is immutable. So as soon as you push up code to the Ethereum blockchain, you've got no way of changing it. Now, there are methods that are currently being developed to actually assist in being able to change code. It's using a proxy contract in which you're able to use that proxy contract to invoke other contracts on the chain, so you can then like patch, move it around without affecting the end user. But then you've got a similar problem of, well, what if you find a vulnerability in that proxy contract, and the whole cycle starts again. So I put a question there. It's just sort of a question to the community, and it goes, in a world where blockchain tech becomes more widespread, how do we as an industry see a responsible disclosure policy happening? And I think that's really important to start thinking about, especially within the Ethereum blockchain. As I think we were discussing yesterday, where one of the cities in Zurich is actually, not Zurich, Switzerland, sorry, is starting to use blockchain tech as part of their voting. And doing electronic voting, as we all know, is quite an interesting subject. Security architects all over the world have tried it. States in America have tried it and definitely failed. And obviously, blockchain tech is the resolution to everything. So we'll see how that goes. So as I said, no results will be specifically discussed. It's just going to be percentages and numbers from here on out. So we're just going to dive straight into some of the results. That didn't work. Cool. So as I said before, there was two sets of data. We've got the unique contracts, which we took from all the contracts scanned, hashed the contract code, distinct them, and put them into a new table. So we've got two sets of values. We've got those, the percentage of those and the percentage of on-chain. So we then took the data that we've got and then applied it to all of the contracts that are on the chain. So what we can see is unique contracts that we have is 63% with vulnerabilities. That's pretty hefty amount. We were sort of expecting a fairly high number, but we weren't expecting that. So that's the unique contracts. So that's just the contracts on their own with no dupes. And then if we look at the on-chain contracts, so everything that is currently live on the Ethereum blockchain as of May 2018, which is when the scan took place. So there might have been self-destruct functions that have been called on those contracts between now and then. So, just keep that in mind. We have 38%. So still a fair amount of contracts that are currently live on the blockchain that have vulnerabilities associated with them. And, these numbers can be spun in any which way you like. But key to note, we won't be telling you where those are. So now we're just going to go into a breakdown of the vulnerabilities so you guys can actually sort of know what we looked for. Discussions about how we looked for them and that. But before we do that, here's a quick graph of the date axis along the bottom and then the number of deployed vulnerable contracts. And you can definitely see a sharp increase in vulnerable contracts being deployed into the blockchain. Now, this is just an arbitrary graph. The Ethereum blockchain was barely known in 2015. I don't even think the feature for smart contracts had been fully developed. And you can see a steady increase. And then a decrease in April. It's an arbitrary graph. It just looks nice. So I thought I'd give something a little bit interesting to look at. Cool. So now we're just going to jump into Elliot discussing the insecure random number generation. Sorry.
So basically, we looked at a number of different issues, and we have developed signatures for these as part of the initial proof of concept of our scanner. And one of the first ones is about random number generation. Like random number generation in general is a bit of a tricky subject, and there's quite a lot of cases where insecure random number generators have been used, and we've had quite detrimental impacts when these have been exploited. And yeah, like on the Ethereum in a deterministic environment, developing secure random number generators is really difficult. So yeah, this is one thing that we really wanted to look at. And typically, there's a few different ways that developers are implementing random numbers. So primarily using block hashes or block properties, and then people are also using like patisserie schemes where users commit and reveal numbers as part of like the protocol of that contract, and then also using external random numbers through oracles in the Ethereum ecosystem. For this, at the moment, we've only focused on block properties, and these are quite good in terms of if you're a developer, because you get this number immediately. Like with the other schemes, you're going to have to wait for a callback or for other users to interact with the contract, whereas if you're using block properties, you get these random numbers, or random, immediately, and you don't need to rely on any external parties. So you at least keep the entire system decentralized, you don't break that, but there are other issues that we can see. There's basically four main properties that we see people generating or using as seeds for sources of entropy, and these are block number, which is obviously the number of the current block, or a block, the coin base, and this is the basically the address where the payout of the miner goes to. The timestamp, so this is the timestamp that the miner has, or the timestamp where the block is mined, and the miner has some control over this. And then also the block hash. Typically the block hash is the most common one we see. And there's an incorrect assumption if you look online about when it's safe to use these random numbers, and people assume that only miners can manipulate these values or use them for an advantage, and this just isn't the case. But yeah, people say that it's acceptable to do only if the payout of the contract is less than the block reward. So it doesn't make sense for the miner to throw away the block reward if the contract payout is only, say, half an ether. Whereas in reality, smart contracts can game these numbers very well because the properties, that the seeds are known, so they can pre-compute or compute them at runtime. So this is just an example of how a random number generation might look like. And we take the block number, so this is the current block that's being mined, and we take one away from this, and this gives us a block number. And then we basically call block hash, and we retrieve the block hash for that. And then we do a modulus operation on that after casting it to an integer. And basically this provides us a number between 0 and 9 in this case, which appears to be random. So for each time you run this, the block number is going to be increasing, and it's going to be outputting a number which seems unpredictable. Whereas, like, if you were able to, basically, if you have a contract and you make an external call to this function, you're able to predict what the block number is going to be. You're going to be able to figure out what this hash is going to be, and then you can only invoke the vulnerable contract if it works in your favor. So basically, how do we detect this? So this is what it looks like at the bytecode level. So this is just a disassembly of the EVM bytecode, and we can see up here we have a block hash operation, and this basically takes an argument, which is the block number, and it pushes, well, it takes that, and then it pushes the block hash to the top of the stack. And then basically what we're going to be looking for, the way that you implement this random number, you take this block hash and then you use it in a modulus operation. So basically we can do just a simple test to say if the current opcode is modulus, and then we basically take the two arguments for this modulus operation, and then we check to see if either of the values in these arguments are tainted by the block hash. And if they do, then this is the most probable case is that they are using this to generate random numbers. And this is what we see, like if you look online, this is how this method of generating numbers looks at the bytecode level. So out of all of the results from this, only 0.8% of the contracts were vulnerable, but then we still had 604 unique contracts vulnerable to this insecure random number generation. And given that it's going to be typically used by games or casinos, that there could still be quite a potential impact if people start gaming and trying to cheat these, as they might hold quite a large balance.
Yeah.
Yeah, next slide.
Yeah, next. Yeah.
Oh, yeah, I've got it. So, this you? Or?
No, it's you.
Okay, cool. So with the insecure call, so one of the other issues that we look for, so basically in Ethereum, you can make calls to external contracts. And there's a few ways to do this. Solidity provides 3 ways to do this, which are the address.call.value, address.send, and address.transfer. And yeah, at the UVM bytecode level, these all boil down to a call opcode. And it's basically the way that there's some slight differences in the way they're handled and the opcodes that they generate. But the important thing to note is that all of these methods transfer execution flow to the recipient. And this might not be an issue if you're actually passing or transferring to a account owned by, or like an externally controlled account, which is run by private keys, but you have no control over if this is a contract account, for example. So in this case, you're providing, you're passing execution flow to an external contract, which is potentially untrusted. And this occurs because the EVM doesn't provide a way to transfer Ether without transferring control flow. So basically, one of the issues that we've looked for is using call.value, and this can typically lead to cases of reentrancy. So basically, like the DAO hack, this was from like a recursive call, and it was due to the use of a call.value. And there's a couple of quirks with this. So this function doesn't propagate exceptions to the calling contract. In the case of something failing, it just returns true or false. And it also forwards all of the remaining gas to the recipient. So if we make this call to an external contract, it's going to trigger code execution, and there's no limit on the amount of gas or the amount of instructions that it can execute. So this is just an example of the code. So here we have just a withdraw function, and inside here we do message sender.call.value, and this is going to pass execution flow over, and then just another example there where we basically do the same, but instead of taking the amount that we're trying to withdraw, we withdraw everything. So if we think about how a reentrancy attack might work, basically, if we look here, we have a require, which is basically just a conditional statement, and this will throw if this condition isn't met. So we're just making sure that the balance of the sender is greater than 0, so we are holding some funds for that sender. And then if that's true, we then do a call.value, and we pass over the balance that we hold for this sender. So we withdraw all of the funds. And then after this call, we then set their balance to 0. What happens in the case of a recursive call? So if this gets sent to another smart contract, we pass control to this smart contract, and then that smart contract can then recall the withdraw all function. And what happens then? So we go into when we make this call.value. If we don't pass any message data, then we go back to what's called a fallback function. So this is this function parentheses, and and this is where code starts executing. So then we basically go victim.withdraw all, and that takes us back into this function. And because we don't update the contract state until after this first call returns successfully, or not successfully in this case because we don't check the return value, but until this call finishes, we can basically, this statement is going to still equate to true, and we're just going to keep sending ether to this address until there's no ether left in this wallet. And yeah, this is a contract that you could use to attack a contract which is vulnerable to a reentrancy issue. So in terms of the bytecode level, how we can observe this, so obviously all three of these functions implement the call function, and the gas limit is basically the amount of gas to forward in this call. The address.transfer and address.send, they basically only send 2,300 gas, and it's not enough for, while it does still can pass the execution flow to the recipient, it's not enough gas to make another external call, and it would only be enough gas for them to actually log an event. So it's considered safe against reentrancy because they're not going to be able to do anything malicious. Whereas before, when you do a call.value, on the in the opcodes, basically, so we can see that the first argument to this call is the gas limit, and this gas limit is achieved by invoking the gas operate opcode. So basically, we see this call instruction or this call opcode, and if the first value on the stack is the result of the gas opcode, then we know that this is a call.value operation. So when we looked at the results of this, we found that 54% of all of the contracts at the time we ran this were vulnerable to, or potentially vulnerable to reentrancy, and they were using this call.value. And that equated to 40,316 unique contracts on the blockchain.
Sure. And then moving on to an unchecked return value. So we have a function call of address.send, and generally what we're looking at in here is any function that is returned back to the parent contract not being handled correctly. Sorry, we're going to have to. So here's a quick snippet of code that kind of gives you an idea of what we're actually looking for. So in terms of how this would be executed, a malicious user could pass through an amount. So where am I? Yeah. So they'd be passed through to another contract, and then upon the next contract failing, so they can send it to a. Where am I going with this?
So basically, with the unchecked return value, like if in our contract we're doing a withdrawal, and we basically send this to the caller, sure. Because we're not checking the return value of this, if we throw an exception or say that we are a contract and we don't implement the basically, if the call to that external contract fails, we're not going to check the return value, and then we're still going to decrease the amount of balance that we hold, even if that transaction failed. So we may end up in an inconsistent state where the contract thinks that it's paid out when actually it hasn't, because we're not checking that return value.
Sure. And that we can start to see the bytecode here. So we can see that the call value has been pushed to the stack, and then the actual check is then performed at this point here. So what we do is then we track the call functions, tag them on the stack, and actually their location as well. And at the end of the execution, we can then see if it's actually returned as a check value or not. And then we've written this into a signature, and again scan the chain. And what this has resulted for is that 14% of unique contracts contain this vulnerability, which equates to just over 10,000, just under 11,000 contracts, that actually have this vulnerability.
Cool. So yeah, and one of the other issues that we've looked into so is the use of delegate call, and basically delegate call is kind of similar to like using call or apply in JavaScript. Basically, like we have our DApp user here, and they make a call to a regular smart contract, and inside this smart contract, typically only itself can write to its contract state. But here we basically have library contracts that we pass execution to, and we allow these library contracts to write to our internal state. So it's basically just use like bringing in an internal library, but we trust that that contract is going to we trust it to operate on our own storage. And yep, if we look back to one of the parity hacks. This is the fallback function from their multi-sig wallet contract, and if somebody makes a payment to this wallet, it first just does a check to see if they're receiving Ether or not, and if the message value is if they are sending something, then they do a deposit, and if they don't, they basically forward this the message data, which is the data that's sent along with the transaction, and it's typically basically the first 4 bytes of a hash, which represents the public function to call. So if we're not sending money, then we basically pass this through to the delegate call. So basically we have a wallet library, and this is an external contract, and it has a function called delegate call. And we basically do a message.data. We pass in the data that was passed to this call, and then that allows the library contract to basically look up that. But because this is like controllable by the caller, all public functions in the library are going to be callable by any user within the context of that user's wallet. So that can lead to dangerous situations, and if we look at parity, there was one where somebody killed the actual library contract itself, and one that resulted in the theft of funds. So basically how we can detect this, we have this call data copy, and this basically copies the call data into memory. And then afterwards we have an mload, which basically gets this from memory onto the stack, and then we invoke delegate call, which is then going to invoke the external library. So we can basically look for if call data, basically if the input data for the current call gets copied into memory, we know the location in memory that it gets loaded into. And then we do the mload, we pull out that data from the memory, so we know that it was a call data, and then that gets passed into the call parameter for the delegate call. And 6% of functions we found to be using delegate call, and that equates to 4,562 of the unique contracts that we looked at.
So moving on so it's all well and good having this data. We now have percentages knowing what vulnerabilities exist, but what can we do? I suppose this is more of a community thing than anything. But as I mentioned earlier in the presentation, the code is law. Actually, I don't think I mentioned this, but on Ethereum, so the code is immutable, and the Ethereum mantra is code is law, which is kind of where they want to go with this. But that makes it really difficult for when vulnerabilities have been found for changes to be implemented. So what else can be done? We could look at the human who's actually developing these contracts, and we can provide education. So the NCC DAS, which is the Distributed App Security Program project. So it's the distributed application version of the OWASP that NCC have created. Open Zeppelin have provided a number of libraries that are able to be used by developers, so they could just call the Open Zeppelin Zeppelin libraries. And then there's Securify, which actually provides an online tool similar to this, which will provide formal verification of smart contracts. And then you can also look at the SDLC and improve the tooling as part of the SDLC lifecycle, so potentially having a number of applications that provide bytecode analysis or static analysis of the code as part of your SDLC workflow, so part of your build or that kind of thing. And Remix is definitely going a long way to help with this, which is the official development tool. Definitely check that out if you've not seen it. And then just into a quick bit of future work. I know we're running out of time. So we're going to definitely continue the work of Treacle Mine. We're going to add more rules for vulnerabilities. We're looking at implementing the storage and memory in the emulator. Potentially looking at fuzzing, see what we can do. Definitely a dashboard for continual scanning of the Ethereum blockchain. So what we want is a website that we can look at that is just going to continually show you stats for vulnerabilities, the percentage-wise of what's there. And then we're also looking at a web interface for ease of use and reverse engineering. So at the moment, it's just a command line interface that returns a JSON, and then we can do with that what we please. And here's just a couple of potential screenshots of what the tool might eventually look like. Pretty simple. Put in your bytecode or potentially your contract address, and then it gives you your disassembly.
Yeah, so this is just what it currently looks like, but yeah, look, we've not integrated all of the security and the scanner into this bit as well, and we're also just working on the graph view at the moment, but this will be released with the tool, and well, yeah, you can either paste in your raw bytecode or a contract address, and it will go ahead and provide you with an online disassembler and run the tool against these contracts.
Brilliant. So thank you very much. We hope you've enjoyed our talk, found it insightful or interesting. We'll be accepting some questions I think Tom's going to be dealing with.
We have a little bit of time for questions. You guys almost hit the limit. Well done.
Almost.
Well done.
Yeah.
You guys like to use your time, huh? Cool.
I know. I'd just like to say thank you. This is my first time talking, so I'm a bit flustered in the middle there. But
no, it's cool. Thank you very much, guys. That was a really technical, very in-depth talk, and yeah, that's what we want to have at these kind of conferences. Obviously, really see people showing their research on how seemingly insecure a lot of contracts are out there. Anyone have any questions? Quickly, we have a couple minutes, so any specific questions anyone has? All right, awesome. Make it as hard as possible. I don't like these guys.
So out of all those vulnerable contracts, how many were empty and how many were exploitable, basically? Or did you not
we can't tell you that.
do those kind of statistics?
So we didn't actually go down into that sort of granular level, purely because if I could skip back through, but there are about, just off the top of my head, I think it was 59,000 empty contracts, which could have been from out-of-gas exceptions or self-destruct functions that were within the code. But what we didn't do was, due to the size of contracts, is we took a slither of contracts to ensure that the tool was working as intended. But what we didn't go ahead and do is sort of make a log of what was exploitable and what was not, because then we get into the realms of, well, how do we then disclose this information? Obviously, we're not going to put it up on a presentation and have it out in the world, because that puts us in a sticky situation. But definitely we'll be looking at that in the future, going in and taking some random contracts and working out what's there and what's not. Apologies, it's a bit vague for an answer, but yeah, it's something that we can't really go into.
And I think also, like any vulnerability scanner, you're never going to expect the scanner to provide you like a definitive list of which results are exploitable. You look at the best static analysis out there, and a large amount of the results are still false positives. It might match a specific pattern, but there may be other mitigations there. And without digging into over 70,000 contracts manually, it's going to be difficult to provide which ones are specifically exploitable.
Cool. Any other questions? All right, still got time for a couple more there.
Thanks for the nice talk. You showed this one graph that shows the increase of vulnerable contracts that have been launched, right?
Yes.
So I'd be interested in seeing the numbers of the overall contracts that have been launched in comparison. So is it that there's more and more contracts, like the fraction of contracts that's launched, is it getting more vulnerable, or is this just a matter of the fact that we are seeing more and more contracts overall?
Yeah, I think it's the second point. We're definitely seeing a lot more contracts being submitted to the blockchain. I mean, you know how it is. So for the likes of Remix, for example, it gives you a fairly simple boilerplate contract. people go, oh, Ethereum, I want to start my development. They'll go on and they'll just immediately compile and push the boilerplate straight to the live blockchain. So you'll see quite a spike in contracts that don't really do anything. But then for those that are vulnerable, yeah, we are seeing a sort of an increase. I wouldn't say the increase is percentage proportionate, so it's staying relatively flat, but you do get some spikes. I mean, it's kind of hard to say. It's kind of, as the tool gets more, as Ethereum gets more popular, it's definitely going to see more vulnerabilities, but then we're also going to see more contracts, so the percentage is probably lower. And the space has seen quite a lot of development in security tools and knowledge and spreading that knowledge, which is really great. And talks like this and other conferences are definitely helping spread the word and definitely getting the developers to think in a secure way, because immutable code not being able to be modified as soon as it's there, that's it. And you've got to make sure that code is secure and is not going to cost your clients or customers money at the end of the day.
I think as well, like with the adoption of things like Open Zeppelins, like interfaces for like ERC20 tokens, so like that could have had like a significant drop in vulnerable contracts deployed. So if people previously were implementing these standards themselves instead of using secure reusable frameworks out there, like when these people adopt these frameworks, I imagine that vulnerabilities are going to drop.
But again, it does come down to promoting those frameworks and having the developers know about them. So the more we can get out there and say to developers, hey, look, these secure, audited libraries exist. Please use them. Don't reinvent the wheel. No one goes and writes their own hashing algorithm or like cryptography, because there's plenty of clever people that have done it and it's been peer reviewed. So we should definitely promote that sort of mindset. And it's not something to be ashamed of that you're using a library. And by all means, implement the ERC tokens on your own, but if you push it to a live blockchain and actually use it for production data, you're walking a fine line.
Cool. Unfortunately, I think we're out of time for this one now, but thank you once more, gentlemen. It's been very, very interesting, and yeah, thank you very much once more.
Brilliant. Thank you very much for having us.